Greetings. This is Michael Reed, and I'm the author of this new paper which I'm going to present today, which is about the multilinear Lie bracket recursion formula. So this basically presents a multilinear Lie bracket which is optimized by a Lie bracket recursion formula, which I'm presenting here as a new idea I'm thinking about. So if we, as a prerequisite, consider sigma as an element of a symmetric group permutation such that epsilon of sigma is minus 1 to the k of basically k transpositions, with the epsilon function being the sign of the permutation. So if we have that as a starting point, then we can define the n-linear Lie bracket using this following definition, as where we take, n of these Lie algebra elements, and then we take the sum over all the permutations of by evaluating them in this way, basically using the sign of the permutation. So this is analogous to an antisymmetric, an antisymmetrization, or just a general, commutator. This is the generalization, how you would generalize it to the n-linear case, where typically only the bilinear case is considered. But today in this new paper, we're considering the most general form that I can think of, which is if we define it in this way. And I don't typically see people defining the Lie brackets like this, but this is a natural generalization of it. So we can take a look at the antisymmetric property, and basically the multilinear Lie bracket is antisymmetric. So if we apply permutation rho on the inputs of the n-linear Lie bracket, then the result is basically the sign of the permutation times the Lie bracket in its natural order. And the proof of that is fairly straightforward and based on standard principles, which can be also applied to the Lie bracket. So there's this, I haven't seen it applied to the Lie bracket specifically like this, but this is fairly natural, to apply it to this. So so we do this here. We take the permutation and we can just compose them like this. Now we have sigma rho. Now we apply the definition 1 basically, but we apply it to the composition of sigma with rho basically. And if we follow that to its conclusion, if we factor out another epsilon, another sign of rho here, such that we change this sum here, then this is basically a sum over sigma rho, which is just another sum over permutations. And this is just again the definition of the n-linear Lie bracket. So it's true basically, but now we have this extra factor of the sign out front. So the sum is equivalent, so the Lie bracket, the n-linear case, is anti-symmetric, just as we hoped it would be. So that's not too surprising and follows fairly straightforward from the definition I gave here. Now we come to the interesting part of the paper here, and that's the Lie bracket recursion. And this is a new idea I came up with for this n-linear Lie bracket, which provides a recursive formula for expressing the n bracket, or the n-linear Lie bracket, as a sum of n-1 linear brackets. And so what this theorem says is basically, if you have this n-linear Lie bracket, you can express it as a sum of these, you know, of over I from 1 to n of, you know, x of I applied to an n-1 bracket, where we leave out I as the index, and then we add the sign of the transposition out front here, which is required for factoring it out here. So this is a really nice formula, which is reminiscent of the Koszul rule for Grassmann algebra, but this is for Lie brackets, so this is a little bit different, and so a different application, different context, and this is a new formula that I haven't seen mentioned before, so I thought I might discuss this here and publish this. So how do we prove this result, basically? So I have the proof of it here. So if we define rho I of sigma as a permutation, then where I is an element of 1 through n, and sigma is a permutation of n-1 size, basically, then we define rho I of sigma as a permutation like this. It takes I and 1 through I minus 1, and then I plus 1 to n, and it transforms it to sigma 1, sigma I minus 1, I, and then sigma I plus 1, sigma n. So this is a very nice definition which will help us prove this result, this theorem, in terms of the definitions I gave above. So basically, what we'll have is this. We'll take this this formula here, and we'll verify that it's equal to this. So we'll take this sum here, and we're going to substitute for this n-1 bracket the definition of the Lie bracket as a sum over the permutation. And so we take the n-1 permutation group, and then we take the sum over it. So this is nothing unusual, except for that it's n-1, leaving out the ith index, and then we just plug it into this formula, and then we're going to verify that this is indeed equal to that. So what we can do is we can move this inside of the sum, basically, because this is just a sum, so we can move this on the inside. So now we have a double sum like this, and we moved this just to the inside here, inside of the second sum. And then what can we do? Well, now we can apply this definition of this rho I of sigma permutation, and we can now permute these terms using rho I of sigma applied to, 1 to I minus 1 and so on. And this would be equal to that, due to this nice permutation that we've defined, rho I of sigma. And now this was a sum, a double sum from I equals 1 to n over all the permutations of n minus 1. And so it's like a double sum over I and sigma, the integer and the permutation. But because now we have they all share the same permutation, rho I of sigma, we can contract this sum into a single sum over the n permutations of rho I of sigma, all of them. And now we have this permutation, and now what we have is basically the definition of the Lie bracket, the multilinear Lie bracket. This is just a definition I gave in the beginning, but now it's over rho I of sigma, which is just the same as, this is just like the theorem of the antisymmetry we talked about. And so we can substitute the right-hand side to apply the antisymmetry permutation, rho I of sigma, and this implies the theorem. So Lie bracket recursion is a valid theorem, and I've shown you the proof here of how this actually works. And it's all thanks to the choice of permutation, rho I of sigma, and applying it using the double sum and the antisymmetry theorem. So this is a new result, I think. I haven't ever seen this result applied to a multilinear Lie bracket, although this is similar in, it's a similar style of formula that's found in, other branches of algebra, such as the Kosul complex of the Grassmann algebra. But this is this is in a different context. This is for Lie algebras, and so this is the multilinear Lie bracket, and it's a recursive rule. So we're gonna look at some examples now to see what the actual examples look like. So we're gonna just take a look at the one linear case, which is trivial. So if we just apply a one linear Lie bracket to x, then it's just equal to x. It's just a sum. It's just only one way to permute it, and there's 0 evaluations. And it's one linear because if we take two scalars and two elements, then we can, apply the linearity rule to it. And it's one linear. Now, if we take a look at the two linear case, this is very standard and traditional Lie bracket. This is the bilinear case, which has been discussed in the literature for a long time. And this is the original definition of it. So if we apply the recursion rule like this, what we end up with is this, basically, x of y minus y of x. So that's very standard. And this is bilinear, so we can do the same thing defining the scalars and checking how we can pull the scalars and the addition out of here through the multilinearity. So if we just follow the standard principles of multilinearity or linearity here, then we can factor these out and make this a sum. So that confirms it, that we can do this for both cases, basically. And so that means it's a bilinear Lie bracket, and it uses basically 2 evaluations or 2 factorial. And this is very well known, but this is one of the simpler examples. And now we go on to look at less traditional cases. This is the ternary Lie bracket, or the trilinear, or the 3 bracket, which is defined by 12 evaluations. So if we take the definition that I originally gave at the beginning and apply it to x, y, and z, then we have, x of y of z minus x of z of y plus y of z of x minus y of x of z plus z of x of y minus z of y of x. And alternatively, if we apply the Lie bracket recursion, this results in 6 evaluations, which is 3 factorial. So we think about it like this: it's now x of the Lie bracket of y and z minus y of the Lie bracket x of z and plus z of the Lie bracket of x and y. And now we can apply recursively the bilinear Lie bracket with the trilinear one. And so this can be verified by inspecting this formula and expanding it out. And what's nice is that instead of 12 evaluations, this only uses 6 evaluations. So it's twice as efficient to use this recursion formula for ternary Lie brackets instead of the original definition. And of course we can prove the trilinearity of this ternary Lie bracket, and this just follows the same principles as for the bilinear case, but now we have to check 3 cases to pull out these scalars and to check the algebra of it. So I've actually went ahead and written out all 3 cases if people want to really convince themselves that this is trilinear indeed. And it is. I've written it using the recursion rule, so we can have lambda x1 plus mu x2 of the bracket of y and z, and minus y of this bracket and z of this bracket, and you just apply linearity. It's more terms you have to write out now, but it's the same principles, and it proves the linearity in each component, and the 3 cases make it a trilinear Lie bracket basically. So that's just that's just how it is. So it's pretty straightforward, and actually this proof is made shorter by applying the recursion rule, because I used the multilinear Lie bracket recursion rule, which I proved, in order to simplify these proofs, because without that I would have had to write even more terms here. So this would have been a proof that would be twice as long without the recursion rule, but by utilizing the recursion rule, this proof is now half as long as it would have been by reducing the evaluations by half basically. So it's nice to be able to have the multilinear Lie bracket recursion, that it demonstrates that this proof can be shortened. Although this is a fairly trivial proof, it can be shortened, by the knowledge of the Lie bracket, the multilinear Lie bracket recursion, which I proved. So that helps simplify things. So that's the trilinear case. And now we can extend to the four linear case. So the leave 4 bracket is defined by 72 evaluations, while the application of the Lie bracket recursion results in 24 evaluations, which is 4 factorial. So we notice that each time we increase the order of the Lie bracket to another higher order linearity, we just multiply it by another by the number that it now is. So it's a factorial. That's the number of evaluations. If you use my Lie bracket, my multilinear Lie bracket recursion formula, which I proved, then this is a new formula which I showed, which simplifies the number of evaluations. So this is 1/3 of the evaluations that the original definition of 72 evaluation has. So what does it look like? So in terms of the recursion formula, this is what we would end up with. We have w, x, y, and z equals w applied to the trilinear bracket x, y, z minus x applied to the trilinear bracket w, y, z plus y applied to the trilinear bracket w, x, z minus z applied to the trilinear bracket w, x, y. And proof of the four linearity follows similar principles as previous examples, and this is left as an exercise for the reader. Now there'll be 4 cases, and it's just going to be very similar to what we showed before, but the proof is going to be 3 times shorter if you apply Lie bracket recursion, because then you don't have to do 72 evaluations, then you only need to do 24 evaluations thanks to my Lie bracket multilinear Lie bracket recursion formula, which I proved. So that's if you wanted to actually do this exercise and prove this, you can actually speed it up, make it 3 times shorter by knowledge of my Lie bracket recursion formula. Now we're going to actually prove the Lie bracket recursion formula for this 4 bracket. So if we apply the definition for the bracket of w, x, y, z, we basically have all these permutations of w, x, y, and z. So we have w applied to x, applied to x of y of z, and w applied to y of z of x, and w applied to z of x of y, and so forth. X applied to w of z of y, and so forth. And what we'll notice is there's some nice patterns here. First of all, these are all the positive terms, and then I have all the negative terms here. So I just sorted this in such a way so that we can have all the subtractions in one segment here and all the additions over here. And if you observe, we have basically these W's on the outside here, then we have the X's, then we have the Y's, then we have the Z's, and same for the minus signs. We have the W's, the X's, the Y's, and the Z's as on the first term here. And now what we can do is this plus and this Wx of y of z and this Wx of z of y can be replaced by W of x of the bilinear bracket yz. So that removes this minus term here. Now we combine these two into a single term, and now we can combine these two into a single term here, W of y of xz, because we have zx and xz, right? So, but now we need a minus sign here. because we want to have minus wy of xz and plus wy of zx. So now we have to assign the minus sign, wy of xz. And the Lie bracket recursion formula, which I gave and proved, it helps us understand this alternating sum of minuses and pluses. And now we have plus again. We have wz of xy and wz of yx. And we can replace the sum of those two with wz of the commutator of x and y. So that takes care of the w's. That reduces the number of evaluations by half. And now we have just one row of the w's, one row of the x's, one row of the y's at the beginning, and one row of the z's. And you'll notice there's this alternating pattern. Now we have minus x plus and minus, and here we have plus and minus and plus and minus and plus and minus. So there's this kind of alternating alternation. It's like a double alternation. And that's due to the recursion of the multilinear Lie bracket recursion formula, which I proved. So it not only alternates in one way, it alternates in multiple ways. So it's because of the recursion, basically, because it recursively alternates in the sign. And now what can we do is we can observe that w of x of the commutator yz minus w of y of the commutator of xz plus w of z of the commutator of x of y, well, that's just w applied to the trilinear bracket xyz. If we go back to the trilinear case, right, we had x of y of z and y of minus y of xz plus z of xy. Now we just have to imagine that there's an extra w on the outside here. And so that was the trilinear case. So these three terms, it's just the trilinear bracket xyz with w applied on it. And now each row is like that. So we have x with wyz. So we have wyz, the trilinear bracket of that, but with minus x on it. So this is alternating in the sign again. So we have plus and minus and plus and minus. So there are many alternating signs here. But this is just following the multilinear Lie bracket recursion formula, which I proved on the first page. So we apply this to the w, the x, and the y, and the z. Now we have these four terms, and that's the 4 bracket. W, x, y, z is a sum of this 4 terms of trilinear brackets. So we can compute the 4 linear bracket in terms of trilinear brackets, and the trilinear brackets can be computed in terms of regular Lie brackets, and so on. So this is the multilinear Lie bracket recursion formula, which I've proved here in the beginning. And hence the recursion formula reduces the evaluation count by 1/3. So we can simplify things. And for the complexity of 72 evaluations and reducing it to 24 by 1/3, that's a significant reduction in evaluations. So that's the multilinear Lie bracket recursion formula proof is really, handy, because it allows us to do these multilinear Lie brackets and reduce the number of evaluations. Now let's consider the 5 linear case. So the 5 bracket is defined by 480 evaluations, while application of Lie bracket recursion has 120 evaluations, which is 5 factorial. So what does this look like in practice? Well, if we have a 5 bracket of v, w, x, y, and z, then we have v of the 4 bracket w, x, y, z minus w of the 4 bracket v, x, y, z plus x of the 4 bracket v, w, y, z minus y of the 4 bracket v, w, x, z plus z of the 4 bracket v, w, x, y. And as with the principle of the multilinear Lie bracket recursion formula, which I proved here at the beginning, the 4 bracket can be recursively obtained in terms of the 3 brackets, and the 3 brackets can be recursively obtained in terms of the 2 brackets, and so forth. So it reduces the number of evaluations by a quarter. So we have 1/4 of the evaluations by applying the multilinear Lie bracket recursion. So the proof of the 5 linearity follows the similar principles as the previous examples and is left as an exercise for the reader. And so again, we can, if you were to carry out this exercise of proving the 5 linearity by going through all the cases, you could make the proof 4 times shorter because you only need 120 evaluations instead of 480 because of the multilinear Lie bracket recursion formula, which I proved. So yeah, that's very nice. So let's actually dive into proving this recursion formula for the 5 linear case, just to expand it out and see how it expands out. So what we have is we have v, w, x, y, and z, and we apply the multilinear Lie bracket recursion. This time we're going to apply it in the opposite order. So we're going to take this result here and we're going to expand each of these terms in the sum in terms of trilinear brackets. So now we have v of the 4 bracket w, x, y, z is expanded into these 4 terms. V of w of the trilinear bracket x, y, z minus v of x of the trilinear bracket w, y, z plus v of y of the trilinear bracket w, x, z minus v of z of the trilinear bracket w, x, y. And similarly, we can apply for minus w of the 4 bracket v of x, y, z the same expansion in terms of trilinear brackets, and then we end up with those 4 terms. And same with each of these. So now it's for plus x and minus y and plus z. So we end up with these alternating alternations of signs, of sums of these different brackets, permutations of lower order brackets, and we have 5 rows of that. And so now what we can do is we can still expand this further by expanding the trilinear bracket, right? So now we have v of the 5 bracket of v, w, x, y, and z can be expanded even further. So now we can expand it in terms of bilinear brackets. We can do v of w of x of the commutator yz minus v of w of y of the commutator xz plus v of w of z of x, the commutator of x and y. So that's this first trilinear term expanded out, v of w of x, y, z. This first row is just expanding that term. And so each row here is expanding one term here. So for each single sum term, we're expanding into a whole row. So we end up with a row for each term. So each trilinear term gets expanded into a sum of 3. So, and then we have the alternating sum. And I'm not going to say all of these, but then you have basically 4 rows with for the v's, because we had 4 terms here. So we get 4 rows of that. Then we get 4 rows for the w's, 4 more rows for the x's, 4 more rows for the y's, 4 more rows for the z's, with the properly alternating signs of the sums. And yeah, so that already takes up a lot of space, a lot more space than this nice formula in terms of 4 brackets, right? So the Lie bracket recursion formula really allows us to express what a 5 bracket, like a multilinear bracket with 5 linear case. It means we only have to write it as a sum of 5 terms involving the 4 brackets. And if we previously defined the 4 brackets, it just goes recursively back. And so we can we no longer need these really complicated sums of all these possible terms of permutations, but we can write it very neatly in a nicer way. So the final step of the multilinear Lie bracket recursion is left as an exercise for the reader. So if you wanted, you could expand this even further. There would be twice as many rows if you expand the bilinear bracket here. So we don't have enough space to fit all those on a single page. So we're not going to do it, but we're going to leave this as an exercise for the reader. And as a result, the recursion formula reduces the evaluation count by 1/4. So what are the corollaries of this multilinear Lie bracket recursion? Well, the main definition of the multilinear Lie bracket has n factorial times n minus 1 evaluations. And the advantage of using the multilinear Lie bracket recursion formula, which I proved on the first page, that only has n factorial evaluations. So if we compare these two, that means that the multilinear Lie bracket recursion is more efficient by 1 over n minus 1. So this generalizes to any higher order multilinearity for Lie brackets. So we can do any kind of n bracket and make it more efficient in terms of evaluations by 1 over n minus 1 by applying this multilinear Lie bracket recursion theorem or formula, which I proved. So my proof can be really useful, I think. So in conclusion, the presented multilinear Lie bracket definition properly generalizes the bilinear Lie bracket to the n-linear case, while the proof of the multilinear Lie bracket recursion enables optimizing evaluations by 1 over n minus 1. The multilinear Lie bracket recursion is analogous to the Koszul complex of the Grassmann algebra, although it is fundamentally different due to the multilinear Lie bracket being non-associative, unlike the analogous exterior product. The order of n-linearity is not restricted by the dimension of the underlying vector space. Instead, the multilinear Lie bracket is limited by the order of differentiation, or unlimited by smoothness of the coefficients. So that's it basically. This is just kind of a quick result, a quick paper. I wanted to get this out there to show this to people, and I'll just go back here to the Lie bracket recursion formula and my proof. So this is my personal proof of this. I haven't seen people talk about this particular proof or this particular Lie bracket recursion anywhere else before, so I figured I'll write this proof down and show it to the world. So yeah, this basically allows you to generalize the bilinear Lie bracket to the n-linear case, completely multilinear, and the recursion even simplifies the number of evaluations that you need, and it makes it nicer to write down the definition of each higher order bracket in terms of the lower order brackets as just a sum over 1 through n, you know. So you just take a sum of 1 through n of some lower order brackets, and the proof is in the pudding. You can yeah, so that's basically my multilinear Lie bracket recursion formula. I don't think I think this is my original result here. Although it's analogous to some other results in mathematics, but this is for Lie brackets. This is in the context of Lie brackets, unlike, you know, other contexts. So this is for the fully non-associative Lie bracket. So it doesn't have to be associative, like the Grassmann exterior algebra and the Koszul complex. That would be an associative, you know, context. This is a more general for Lie brackets where it's non-associative, and it's more general. And yeah, this is my proof of it. This is the multilinear Lie bracket recursion formula by myself, Michael Reed, the author. So yeah, that's it basically. Thanks for taking a listen or taking a look at this, and yeah, I'll just end this here.